This video is about graphing quadratics from standard form.
So quadratic functions are those with an x squared in them, and when graphed on the coordinate plane, they make a shape that looks like the letter U almost, and it's called a parabola. So the shape that they take is called a parabola. So the parent function, y equals x squared, is going to have the point 0, 0 on it, because if you plug in 0 for x, you would get 0 for y in this function. And then the rest of the function, when you connect the dots, will look something like that. It's supposed to be a nice symmetric U shape, and that shape is called a parabola. And of course, you could take it and shift it around. I could slide it to the left or to the right, or slide it up or down, or stretch it out, just like we've been doing with functions all year. Parabolas have three important features: a vertex that you need to be able to find and identify, an axis of symmetry that you need to be able to find, and then one real, two real, or no real x-intercepts. And those are sometimes also called the roots, or the zeros. It's a fancy way of saying, where does it cross the x-axis? You need to be able to identify that point. So on the graph of a parabola, and let's do maybe a reflected parabola that's also been shifted to the left and shifted up a little bit. You need to be able to identify where the vertex is, and that's going to be this point. So the vertex is a point. It's a point where it turns around. It goes from increasing to decreasing or decreasing to increasing. Sometimes it's called the maximum point, sometimes it's called the minimum point also. Depends on if it's the top of the U or the bottom of the U. You need to be able to identify where the axis of symmetry is. And the axis of symmetry is a vertical line. It's invisible, but it goes right through the vertex, and it's the line that would divide your parabola into two symmetric halves. So if you were to fold the parabola over that axis of symmetry, it would line up with itself. It's called an axis because it's a line, just like the x-axis or the y-axis, and it is an invisible feature of every parabola that you need to be able to find. And then x-intercepts are where a function crosses the x-axis. Parabolas tend to have two, as this parabola does, crosses the x-axis in two different places. But there are some cases, I'll put these smaller over here, where the parabola ends up only having one, and that's if the vertex happened to be right on the axis, so it would only touch it one time. And then there are cases where the parabola has no x-intercepts that are real numbers, and that would be if the entire parabola was below or above the x-axis. The standard form of a quadratic function, which is the form we're going to use for this whole presentation, is ax squared plus bx plus c. So this is when it's given to you in this form. We're going to practice how do you graph from this form. So I've said that the vertex is really important for graphing a quadratic, which makes sense because it's the middle of the U, and you want to be able to find that starting point first. To get the coordinates of a vertex from standard form, you're going to use this formula, which looks something like the quadratic formula, but without the big square root part. And what that value gives you is the x value in the center of your parabola. So it's the x value of the vertex. So for this function, we don't have any numbers in this function, so we'll practice that with numbers on the next slide. Once you've gotten that value, this is just an x, then you plug it back in to f of x, which is the function, in order to get y. And that's how you always obtain a y value for a function, right? So you'll take a negative b over 2a to get the x, you'll plug it back into the function to get y, and then together, that x and y are the coordinates of your vertex. We'll practice it with numbers in just a minute. The equation of the axis of symmetry, it goes right through the vertex, remember. The axis of symmetry is that dotted line that goes right through the middle. And it's a vertical line. Vertical lines have equations that start with x equals, and the x value of the axis of symmetry is going to be the same as the vertex, because it goes right through the vertex. So you'll use that same formula, or really you probably already will have the number because you've already gotten the vertex, to know where the axis of symmetry is. And to get the coordinates of the x-intercept for any quadratic function, or any function at all, you change y to 0. And where's y in a function that looks like the standard form written above? It's the f of x. So really, it would look like this. And then you would have to solve the resulting equation. Now you know how to solve a quadratic equation when it says equals 0. You have a bunch of tools to do that. You can use factoring, square root sometimes. You can use the quadratic formula if you can't use any of the other methods. And as you know, sometimes those answers will come out real and sometimes they'll come out imaginary. So as we previewed on the slide right before this, Sometimes you're going to get 2 answers, sometimes you're going to get 1, and sometimes you're going to get only imaginary answers, which of course you can't see on the graph. Let's practice doing both of those, or all 3 of those things with numbers. So here's our first function in standard form, y equals x squared minus 4x plus 3. It's asking us to find 3 things: the vertex, the axis of symmetry, and the x-intercepts. Let's start with the vertex. To get the vertex, we do negative b over 2a. So let's just find the x value. So negative b here is going to be positive 4. And 2 times a is going to be 2. So 4 over 2, which is 2. Remember, that's only an x value, so I like to write it like that, parentheses 2, comma, to remind myself that I'm now about to fill in the y value that goes with it. In order to get the y value that goes with it, we take that answer that we just got and plug it into the function. So I'll show that work here. We got 2 for our x. We're going to plug it into the function and evaluate. 2 squared is 4, minus 8, which is negative 4, plus 3, which is negative 1. And so that means that the coordinates of the vertex are 2, negative 1, x comma 1. The other thing it wants is the axis of symmetry. If you've already got your vertex, the axis of symmetry is really easy. It's a vertical line that goes right through it. And so it's just going to be x equals whatever the x value of your vertex is, which was 2. And then to get the x-intercepts, you have to do a little bit of work. And that's to change the y to 0 in the function, and then find a way to solve it. This is a nice factorable equation. So when you can factor, it's always the preferred method. You're looking for something that multiplies to make 3 and adds up to negative 4. It will be minus 3 and minus 1. And then you use the zero product property to solve each of these equations. So x will equal 3 and x will equal 1. I'm going to write my answers to these as coordinates. But you could also, in some cases, it's going to be fine to just leave it as x equals 3 and x equals 1. But sometimes you'll be asked to write them as coordinates, so you might as well get in the habit of doing it. Because if the next step was going to be to graph this, you would want to plot those points on the coordinate plane. So you might as well have them written as points. In the interest of time, I won't do this second example, but you're going to follow the same process. You're going to do negative b over 2a, take your result, plug it back in to get the y value. Axis of symmetry is going to be the same as the x coordinate of the vertex. And then to get the x-intercepts, you factor it if you can, and use the quadratic formula if you can't. To then graph quadratic function, which is logically where we were headed, you want to start by graphing the vertex. So you'll have that center point, and you'll plot that first. You should write these steps down if you're taking notes. The next thing I like to do is sketch the axis of symmetry as a dotted line. And then I just need to find a couple more points, 2 more points that are on one side of the axis of symmetry. And then I can just reflect those 2 points across the symmetry to find the other 2 coordinates that line up with it. And then you have 5 dots that you can connect to make the U. So here's the steps. Pause and record these, and then we'll go on and actually do this with an example on the next slide. So here's the example. We're going to graph it showing at least 5 points, including the vertex. So the steps I said were, you want to find the vertex first by doing negative b over 2a. And you'll plug in positive 2. 2 times a half is just 1, so this ends up being 2 divided by 1, which is just 2. Remember, that's only the x value of the vertex, so you'll need to plug that back in to find the y value that goes with it. So I'll plug in 2 for everywhere I see x. This will be half of 4 minus 4 plus 3, so negative 2 plus 3, which is 1. So the vertex here is located at 2, 1. And the steps for graphing said to plot that point first. So I'm going to plot 2, 1. And that's going to be the center of the parabola. The next thing it said to do was sketch the axis of symmetry. So as a light dotted line, go right vertically through your vertex. The equation of that axis of symmetry is going to be x equals 2. I like to write it at the top of that line, have it labeled. And then it said to find 2 more points that are on one side of the axis of symmetry. So I like to show it just a very short little xy table, an input-output table. Any 2 inputs, which are x values, that I want on one side of this axis of symmetry. I would say that if the axis of symmetry is at 2, the easiest 2 numbers that are right next to that to plug in would be 1 and 0. So on my input table, I'm going to choose 1 and 0. If you're not sure how I got those numbers, just go either way. From that x equals 2, you could either then try x equals 3 and 4, or head the other direction and x equals 1 or 0. I think it's easier to plug in 1 and 0, so that's why I'm doing those. To plug them in, you put them in the original function in place of x. You can can use a calculator if you need to help you with the evaluation step. This ends up being 1/2 minus 2, which is negative 1.5, plus 3. And I don't mind decimals here because you're going to be using the graph. You're going to be graphing them. And it's a little easier to graph with decimals because you know where to locate them. Plug in 0. I almost didn't need to show work for that at all. It just ends up being 3. And now I have 2 more points that I can plot. 1, 1.5. That would be right about here. And then 0, 3. So it's a little bit steeper right there. And the final step is going to be to reflect those points across the axis of symmetry. So you don't have to do any math to reflect these. You just go to the exact same distance across the axis of symmetry for both points. And once you've got 5 points, which is what the instructions ask for, connected in the smoothest U you can make, and you're going to have to practice making that nice and smooth to get the right parabola shape. These are some analysis questions that you should be able to answer for the function that we just graphed. So this is the exact same function, and we're just going to answer some analysis questions. Concavity, meaning what is the direction that this U is facing? Does it open upwards or does it open downwards? So the graph that we just created showed it looked something like this, and it was opening upwards. Therefore, we would say it is concave up. And even if you don't have the graph, you can always determine concavity just by looking at the sign of the first number, the A value. So if A is positive, then it's going to be concave up. And if your A value is negative, then it's going to be concave down, meaning it will be a downward facing U. So even if you haven't done the whole graph, you can still answer that analysis question. Coordinates of the vertex, we calculated first. That was 2, 1. Equation of the axis of symmetry was x equals 2. That's because it goes right through the vertex. Coordinates of the y-intercept, that's what you get when you plug in 0. So it happens in every function that we've done and every function that you will do. Just get in the habit of plugging in 0 anytime you see y-intercept. And write your answer as an ordered pair to that. So if you plugged in 0, you would get 3, which we've actually already done for this function. And the coordinates of the x-intercept, and of course that should actually be plural because there may be 2, you're going to obtain by changing y to 0 and solving the equation. But I can already tell from looking at my graph that this equation is not going to cross the x-axis anywhere. And that would mean if I was to get these coordinates, they'd be imaginary numbers anyway. So I'm going to go ahead and say that they're not real. Now there is a time and a place for when I'm going to actually want you to give me the imaginary solutions, but that would be on a separate section of this chapter where we're just solving equations. When you're in the context of graphing, you don't need to tell me that the x-intercepts are, plus or minus 2i or something like that, because you can't see them on the graph anyway. So in this case, it's okay to just say no real x-intercepts as soon as you realize that it's not going to have any. More analysis questions. Domain means what are all the possible values for x? And in a quadratic function, it's all real numbers. If you wanted to look at that graphically, this parabola never stops getting wider. It never stops going to the left and to the right. So that means all x values will be included on it somewhere. The range, however, which is all the possible y values, is limited here. The y values here never go below the vertex, and the vertex was at 2, 1. So the range for this function is that y only includes values that are greater than or equal to 1, 1 being the lowest possible y value for this function. It came from the vertex. Local max-min and absolute max-min are really easy for a quadratic function. It's whatever the vertex was. You just need to tell me if it's a minimum point or a maximum point. In this function, it's a minimum point because it's on the bottom of the U, and all the other points are greater than that. So you just need to tell me whatever the vertex is and whether it's maximum or minimum. It is both the local and the absolute for this function. And then intervals of increasing and decreasing are also pretty easy for a function like this because there's one of each. This function is increasing starting from the vertex, right here, and going this direction. It's increasing. And we write our intervals of increasing typically in interval notation. So starting from the x value of 2 and going towards the x value of infinity, this function is increasing. And then it's decreasing on this side of the world, starting from the value of negative infinity and going to the x value of 2. And then without graphing, to determine if a function has a maximum or a minimum value, this is the thing where you're going to identify concavity based on your a value. So if this a value is a positive 2, that means you know your function is going like this. It's a concave up function. So you can tell from just that this function has a minimum value and not a maximum value, right? Because this point right here would be our minimum. It has no maximum because it keeps going up and up and up forever. To get that minimum value, you have to know that that's the vertex. And the vertex is found by doing negative b over 2a, which for this function will be negative 8 over 2 times 2, or negative 8 divided by 4. And then you need to take that value, plug it back into the function. This ends up being 2 times 4, which is 8. 8 minus 16, plus 7, which is negative 1. And this is the actual final answer to this question, because what it was asking you for is the value that is the minimum value for the function. And remember, the function values are y. This was just getting the x value that leads to the lowest possible y value for this function. So the minimum value of the function is just the y value at the vertex. That is it.